All right, so all along we've been saying, suppose sigma is known. And it may sound a little odd that you should know sigma, but here we are making inference about mu. We don't know mu, but we know sigma. So, okay, finally, let's remove that constraint that we know sigma. Okay, so what if sigma is unknown? Here we are. Let's go back to Rice. This time, though, let's keep this bottom tableau. Okay, so now let's look at this bottom tableau and let's look at the variance. It gives you a choice of statistics, variance. Let's stick with our n of 25. And in this one, let's stick with the mean as we did before. Now, what distribution? Once again, let me have fun drawing a population. So it's just some arbitrary population. And I love it when I can draw on this. And there we go. So now we've got the mean of 15.9. But this time what I'm interested in is the standard deviation of 7.45. Now, when we do a sample from this population, it does just like before and chooses a sample for which it calculates the mean. But this time it calculates another sample. So it takes two samples. And with the second one, it calculates the variance. So let's do it again. With the first one, it calculates the mean. For the second one, it retains the variance. And this way, the mean, the sample mean, and the sample variances are independent of each other because they're based on different samples. Let's jump ahead and do all 10,000. And let's not mess around. Okay, so let's just look at the final set of results after we've done this 10,002 times. Now, we've got that the mean is 15.8, and as before, the sample mean, the mean of the sample means is 15.83, and we are fine with that. The standard deviation is 7.2. Here's 1.44. We took samples of size 25, so that's the standard error. Multiply 1.44 by 5, and what do we get? We get about 7.2. So pretty close. This time, though, what I'd like to do is let's look at down here and see what's going on here. These are the 10,002 sample variances. Their mean is 50.05. So the mean of the sample variances are 50.05. How does that relate to the population variance? Well, unfortunately, we don't get the population variance. We get the population standard deviation. So the population variance would be 7.22 squared, which is roughly, it's 50 plus or minus something. What do we got here? We've got that the mean of the sample variances is 50.05. Theory tells us that this mean of the sample variances is estimating the population variance. So the mean of the sample variances is estimating the population variance. So just as the mean of the sample means is the same as the population mean, so too is the mean of the sample variances equal to the population variance. So using the sample variance to estimate the population variance is not a bad thing to do. Now, it may seem like many hours ago, I said to you, we will define the sample variance as 1 over n minus 1 summation j equals 1 to n xj minus x bar squared. And I said to you, I will let you know why we are dividing by n minus 1 and not n. Now I can tell you why we divided by n minus 1 and not n. We divided by n minus 1 so that I can make this statement to you, namely that the mean of the sample variances is equal to the population variance. I can only make that statement if, in fact, we divide by n minus 1 and not n. If we divide by n, then this sample variance will be a smidgen too small. So, promise met. So, what can we do? How do we incorporate all this now? So the answer to the question, what if sigma is unknown? Then take your z. If sigma is unknown, just plug in the sample standard deviation s instead of sigma. And that's how we standardize when we don't know sigma. Now, to differentiate from z, we call this quantity t. So t is x bar minus mu divided by the sample standard deviation divided by the square root of n. This is not as simple as with z. The distribution of this quantity, we need to know how big the sample was. And what we do is subtract 1 from the sample, and we call it degrees of freedom. So we need to retain that too. One other further complication is if we want to know the distribution of this thing, what is the sampling distribution of t? We need to make one extra assumption. We need to make this assumption here that the parent population is approximately normal. So that's the extra assumption. Then I can tell you what the distribution of this t is from sample to sample to sample. So we can set up our confidence intervals and so on. We can make all the inference we want to make, but we need this extra assumption. And this result was due to William Gossett, who did these calculations. It's mostly for small n that he did these calculations. A very, very powerful result. He used the pen name student because he worked for a brewery in Dublin called Guinness. He didn't want his name out there. He was concerned about publishing, and so he used the pen name student. So it's called students t. So here is students t, and for students t we need to know what the degrees of freedom are. So what happens, of course, is in the past, when we knew sigma, we were interested in how did these sample means vary from sample to sample. Now we have to tag along these sample standard deviations. So when we get our t's are going to have a different s every time. So we expect these things to be a little bit more variable. So here's the generic t. It should be a little bit more variable. And indeed, it is. Here is the normal density. So this top one here, that's the normal density. And you can see, and underneath I've got the student t. And you can see here that the tails are thicker for the student. So that means it's going to have a bigger variability. The normal is much more peaked in the center than the student t. So you're going to have more variability with the student t as you do with the normal density. Now, what I've drawn here is about as bad as the student t can get. This is when the student t has 1 degree of freedom, which is also sometimes called the Cauchy distribution. By the time you get to about 30 degrees of freedom, this graph here has actually got 3 curves. The old one as before, the normal density, and the student with 1 degree of freedom as before. But I've also superimposed the student with 30 degrees of freedom, and you see that there's very little difference between the student with 30 degrees of difference and the normal density. So in the old days, we would say, oh, if it's more than 30, just use the normal distribution. Stata doesn't do that anymore because it can calculate things exactly for you. So when it needs to use the student t, it uses the student t with the appropriate degrees of freedom. irrespective of whether it's almost the same as the normal approximation or not.